All right, intermolecular forces. We're going to be going into some grave details. Some will be reviewed from last year. Some will be new, like things to compare. Looking here, we have some different types of like induced dipole attractive forces versus the permanent dipole, which are going to be your polar molecules, and your induced ones are your nonpolar ones that become polarized and therefore can then engage with London dispersion forces. We're going to start at the basics here and then work our way into the newer stuff. Starting here at learning targets. Going to identify IMFs for different molecules. We're going to explain the role IMFs play in determining physical properties of matter. Explain how IMFs determine the phases of matter. And compare relative strengths of IMFs based on the property data given. So we'll be talking about a bunch of different properties that are affected, and of course, yes, this falls mostly under like the covalent, regular molecular type substances here. All right, fundamental difference between states of matters is the distance between the particles. And I love this arrangement here because it's showing you the halogens, and the halogens are a pretty notable group in the fact that you have two of them are gases, one of them is a liquid, and then one of them is a solid at room temperature. So they all have different strengths of their London dispersion forces based off of the atomic size of the different atoms. As the atomic size increases, remember you get more electrons. More electrons are more polarizable, so you get a stronger LDF. But here we have chlorine gas, which is this like yellow-green gas. Bromine liquid is kind of an orange-brown liquid at room temperature. And then, of course, iodine is crystalline solid. But like iodine's melting point is still only like 115 degrees Celsius, so it's not super high or anything. All of these are going to have low melting and boiling points. Okay. But the distance between the particles, the gas one, they're spread out. We assume in the kinetic molecular theory that gases have no attractive or repulsive forces. The liquid bromine, they're going to still be pretty packed close together. They do have some IMFs engaging, so they can still flip and turn and slide past each other, and they will have some kinetic energy and free movement. The iodine, though, the solids, remember they're in fixed position, held by the stronger IMFs. And all they can really do is vibrate in place. So the energy there, they still have energy. They are vibrating. They're in fixed position though. And the only time where matter won't have any energy at all is when you've reached absolute zero. Okay, which is 0K, 0 Kelvin. All right, the state a substance is in at a particular temperature and pressure depends on two antagonistic entities. So antagonistic meaning opposing entities. We have the kinetic energy of the particles. Higher kinetic energy means they're moving faster, means they want to spread out, versus the strength of the attractions between the particles. Stronger attractions want to pull them together. So this is why they're opposing or antagonistic in terms of these two qualities, these two characteristics. Okay? Gases obviously have high kinetic energy, no forces. Solids have the lower kinetic energy, but really stronger IMFs. So IMFs of the solid are always going to be stronger than the IMFs in a liquid, and then we assume the gases have no IMFs at all. All right, like this chart here too to help you review the different characteristics of solids, liquids, and gases. Remember, gases fill their container completely. They are compressible because they have space between the particles. Liquids and solids are not compressible because they're already really close together. And liquids, they have free movement, so they take the shape of the container that they're in. So they have definite volume, but indefinite shape. And then, of course, the solid has definite shape and volume. It really doesn't take the shape of any container because it is its own shape. And obviously, diffusion occurs really slowly through the solid. It'll occur faster through the liquid. And then, of course, diffusion occurs rapidly through gases. All right, intermolecular forces, the attractions between molecules that are not nearly as strong as intra-forces. So when we're talking about intra-forces, remember what falls under intra-forces are ionic, metallic, and covalent. Now, whether it's network covalent or regular covalent, what is a regular covalent? If we're looking at this example, the regular covalent would be the unequal sharing of electrons between the hydrogen and the chlorine. That is an intra force. However, to get the hydrogen chlorides to interact with one another, these dotted lines, those are going to be the weak IMF. And they always draw IMFs with dotted lines or dashed lines to show that they are not as strong as an intra force. Okay? So keep that in mind. All right, these intermolecular attractions, however, are strong enough to control physical properties such as boiling points, melting points, vapor pressures, viscosities, heat of fusion, heat of vaporization values. There's a bunch of them that fall under criteria here, and we will be discussing the properties as data points and how to refer to which one has stronger IMFs. Okay? These intermolecular forces as a group are referred to as van der Waals forces. Van der Waals forces basically says that you have some kind of polarization occurring within a molecule, whether it is a nonpolar substance that does a temporary dipole versus a polar substance that has a permanent dipole, okay, based off of the electronegativity differences. So our van der Waals forces, technically all of these will fit the description. We have London dispersion, which you can also just call dispersion. You don't have to say London dispersion. I go with LDFs, but dispersion forces will also suffice. Dipole, and hydrogen bondings all fit the mold of falling under the umbrella of van der Waals forces. All right, so let's talk about dispersion forces, or LDFs, London dispersion forces. They are forces of attraction between temporary and instantaneous dipoles. They are considered the weakest of the IMF category. All atoms, molecules will form LDFs if they're near other atoms or molecules. So, this includes the noble gases. They have electron clouds, so they can engage with London dispersion forces. So let's look at an example of how this process occurs. Atom A and atom B, we're going to label them as helium. They have 2 electrons, so they match helium's description here. So while the electrons in the 1s orbital of helium would repel each other and therefore tend to stay far away from each other, sometimes it does happen where they end up on the same side of the electron cloud. And that would be what we would call the instantaneous dipole. It just randomly happens, okay? So as you can see here, they're just randomly around their nuclei. And now, for some spontaneous random reason, these 2 electrons end up over here together on the same side. This creates an instantaneous dipole. Now, if it's near another helium, these electrons are going to cause repulsive force on this side of the electron cloud. So those electrons are also going to shift over to the other side. When they shift over to the other side, it creates this partial negative, okay? So at that instant, then the helium atom B is polar with an excess of electrons on the left side and a shortage on the right side. So it creates this temporary dipole. So now, another helium, A, nearby, then would have a dipole induced in it as the electrons on the left side of the atom repel the electrons in the cloud on the helium atom A. Okay, so now we've created the instantaneous dipole from atom B induces a dipole in atom A, and now we have 2 temporary partially charged clouds that have been polarized, and you get now an attractive force between the negative side of one and the positive side of the other. That is your LDF. Now, the second they are far apart from one another, that attractive force is going to go away. So that they're very fleeting. They don't last, okay? They're not very strong. All right, London dispersion forces or dispersion forces are attractions between an instantaneous dipole and an induced dipole, and it really becomes like a cascade effect. So once one induces another, the next one induces the other, and now you have this chain of London dispersion forces that have formed. So I really like this graphic, okay, because it shows where the electrons shift and the polarizability of the cloud. The electrons shift to one side, now your cloud has been polarized. And depending on how many electrons shift to one side will determine the degree of the polarization, which also determines the degree of strength of the LDF force. Okay? So this is a good place to stop. We'll resume next time.